Welcome back to Understanding High School Physics, where I help students really understand physics principles. In this video, I'm going to explain three aspects of momentum: what it actually is, when we should use it, and why the momentum of the centre of mass of a closed system remains constant. But first, let's quickly review objects and systems. An object is like a thing which can have mass and sometimes electrical charge, but it has no internal structure. So we can think of this person in space as an object, and her hammer as an object. But if she can throw the hammer, then there must be able to be forces produced between them. So we consider this a person-hammer system. So what actually is momentum? You might have been told it's something like quantity of motion, but what does that actually mean? And why do we use mass times velocity to calculate it? I encourage my students to instead think of momentum as the product of a force and time. So if the astronaut applies a force F against the hammer for a time t, and we multiply them, we get this. If you're not sure why I'm doing this, I suggest watching my video on quantities and units. So what do we get? The units of mass times velocity. Because internal forces are often not constant, and because mass and velocity are usually easier to measure, we usually calculate momentum using mass times velocity, but to understand how it works or know when to use it, I really recommend thinking of force times time. This is especially important for the idea of impulse, which I might cover in a later video. Vocab time. In physics terminology, whenever internal forces push something apart, it's called an explosion. It doesn't need to be something like a firecracker going off, although it often is. But hopefully you figured out that there's something wrong here. If the astronaut is in space, and she applies a force to the hammer, then the hammer must apply an equal and opposite force to her, according to Newton's third law, right? So the astronaut will be pushed backwards with a force of the same magnitude and for the same amount of time. Therefore, she'll end up with the same magnitude of momentum in the opposite direction. And since momentum is a vector, one of them must be negative. So when we add them as vectors, they cancel each other out. Thus, the total momentum of the astronaut person system is zero before and after she throws the hammer, so the momentum remains constant throughout. In understanding high school physics, I focus more on the concepts than the math, but if you'd like to work through any of the math, please pause the video, and here it is. The same thing would happen, of course, if the speeds were the same in the opposite directions, and she were to catch the hammer. The forces stopping her and the hammer are also equal and opposite, so the changes in momentum for her and the hammer must also be equal and opposite, resulting again in no change in momentum to the whole system. Of course, if a larger hammer with more momentum were thrown towards her at the same speed, then the total momentum would not be zero before or after, so she and the hammer would move backwards together after she caught her. But the total momentum of the system before and after, in any direction, would still be the same. Vocab time again. In physics terminology, this is called a collision. It doesn't need to be something like a car crash, although again it often is. So when should we use momentum? Any time that two or more objects interact with each other and all the equal and opposite forces from Newton's third law apply to objects in our chosen system. So the forces between colliding cars, colliding trolleys in the lab, or parts of an exploding firecracker are all internal forces, so momentum is conserved in all these situations. Friction and gravity are often considered external forces because they're often between an object and the Earth, and we often choose for the Earth to not be part of our system. A classic teaching example is the ballistic pendulum, which can be used to determine the speed of a bullet which is fired into a wooden pendulum of sorts, and then we can measure its gain in height and calculate the initial velocity of the bullet. As the bullet becomes embedded in the wood, there are equal and opposite forces of friction between the wood and the bullet, accelerating the wood and decelerating the bullet. So this process is usually modelled with conservation of momentum and connected with the final velocity of the bullet block system. Then it rises against gravity, converting its kinetic energy to potential energy. This gravity exists because of the Earth, but since the Earth moves such a tiny amount which is impossible to measure, we don't usually choose to include the Earth as part of our system with problems like this. So we can't use conservation of momentum and might use conservation of energy instead. One interesting thing about the ballistic pendulum is that these processes of the bullet embedding in the block and them both rising together actually overlap each other in time, but we can still model the two separately using different physics principles. Let's look at that once more briefly. As the bullet slows down, internal, equal and opposite, friction forces occur between the bullet and the block, so it's a closed system, so we can use conservation of momentum. But then when the whole system rises against gravity, that gravity is an external force because the Earth isn't part of our chosen system. Therefore, we have an open system, so we can't use conservation of momentum and would probably use energy instead. Now let's bring our astronaut back to Earth and to a beautiful snowy field, and imagine that she kicks her hammer along the frictionless ground. Of course, there are weight and normal forces involved, but they all cancel each other out for now. Now let's imagine that we cut a chunk out of the ice and placed it on a pivot, like a seesaw, with the pivot at its centre of mass. Now our skier will kick the hammer, and then let's pause it suddenly and find the new centre of mass. Because the momentum of the person and the hammer are equal and opposite, we can calculate the displacement of each from the origin, which will place at the original centre of mass, after a time t. Here is their momentum, equal and opposite, and here is their displacement, based on this and time. The AP Physics 1 equation sheet doesn't have a formula for centre of mass, but here's the one from Gen-Colli Physics, adapted for the person and the hammer here. Substituting in the displacement we just calculated, we see that we end up with these cancelling out, thus a numerator of 0, meaning that the position of the centre of mass hasn't changed and is still at the origin. We could also use principles of torque and static equilibrium to show the same thing. Let's consider their weight forces, and define clockwise torque as positive, so the hammer produces positive, or clockwise torque, and the person produces negative, or anti-clockwise torque. In a calculation which turns out almost exactly the same as the centre of mass one, we see that the torque created by the person and the hammer cancel each other out, so it's all still balanced, meaning that the centre of mass is still in the same place as before she kicked the hammer. Now let's bring these two scenarios together into a final example, and have her stand on a toboggan or something and throw the hammer away. Just as before, the total momentum of the system will be conserved and its centre of mass won't change. But now let's bring another person in, drop the first person the hammer, and have her throw it to the second person who catches it. And now let's do all that on our ice seesaw thing. If we drop the first person the hammer, well, that's not going to work. So let's consider their weight forces, and as the first person catches the hammer, we'll move the pivot along towards her so that the system remains balanced. Now when she throws it, and when her friend catches it, it will always be balanced, because all the forces involved in the throwing and catching of the hammer are internal forces of our closed system, so the momentum of the centre of mass doesn't change, therefore it stays in the same place. I hope this helped you to understand momentum and to know when to use it. Please leave any questions about this or any other physics questions in the comments if you have any, and I'll do my best to answer them. And if you found this helpful, please subscribe. As always, thanks for watching.